All right, so I want to welcome everyone again for this workshop seminar series. Today we have Dr. Ivo Pasman. Dr. Ivo Pasman got his PhD from Oregon State University. He is currently a postdoc at the University of Reading under the mentorship of Alberto Carrassi. Previously, he helped develop Ensemble 4D VAR for the Oregon coast. He is also currently one of the collaborators with me and Chris Jones. Okay, so today he's going to talk about the computational challenges in operational data assimilation. So without further ado, Dr. Pasman, the floor is yours.
Okay, so this talk is going to be a bit different from the talks we saw over the last few weeks. I haven't got an interesting piece of research I would like to present, but I've got some, I would like to present a review about data assimilation in operational weather and ocean forecasting systems, and then in particular, why it's more difficult than data assimilation in a simple toy model, and what kind of parallelization strategies have been developed to deal with it. So I'll start off with introducing data assimilation, explaining how it's implemented in operational systems, and then I'll explain the basics behind the two most popular data assimilation methods, the Kalman filter and the variational data assimilation, and in the end, there's of course a summary. So the aim of data assimilation is to reconstruct the unknown truth given some guess, usually derived from a numerical model, and some observations, usually sparse and noisy. Now, to illustrate this, how data assimilation works, I would like to show an example using shallow water equations. These equations describe the motion of the ocean at the lowest order, where H, capital H, is the depth of the ocean, the small h is the perturbation of the ocean surface from some unperturbed state, U is the velocity, along the slide, and V is the velocity into the slide. And the important thing is that these equations have a stationary solution, which is called geostrophic flow, in which the gradient and the pressure stemming from the slope in the ocean surface is balanced by the Coriolis force. So suppose we've got some observations of our ocean, the height of the ocean surface, and we want to assimilate those in a model. The naive approach would be just to take the observed value and replace the model value at the grid point closest to the observation with the observed value. There are, however, some problems with this approach. First of all, if we compare the observed value with the actual truth, we see they don't match, and that's because observations have usually have an error on them, and you have to account for that in your data assimilation. The second problem is that observations are sparse in general, and so if you just replace values in your model, you end up with this very non-smooth state, and this is just not how physical fields look. And lastly, if you make a correction like this and you start up your model using your corrected state as initial conditions, then within no time, the correction gets carried off as waves, because the correction doesn't lie in the stable manifold where the geostrophic solution can be found. And that is double bad, because first of all, you lose your correction, and secondly, all these waves they mess up your model forecast. If you, however, follow a proper with proper data assimilation and with a proper data assimilation methods that takes into account the balance in the ocean, it is possible to generate a good correction, as is shown over here with the ocean surface on the left as function from the position and your velocities on the right. In operational weather forecasting, this data assimilation is encapsulated in a series of, in a sequence of windows. In each window, the numerical model is used to generate a multi-day forecast. Then after a few hours, observations come in. Those observations are compared with the forecast. So the forecast serves as the initial guess. And data assimilation then calculates a correction to the forecast. The corrected forecast state is called the analysis. And this analysis is then used as the initial condition for the next forecast run. The observations in an ocean or weather forecasting, in an ocean forecasting system would, for example, consist of the sea surface height as observed along a track by satellites, sea surface temperature, once again from satellites. Within a weather model, you would get temperatures of your atmosphere, and then velocities and/or precipitation from radar stations, and many more observation platforms like floats or weather balloons or just weather stations on land. And these operational models solve a set of differential equations on a finite number of points. And these points are located on the vertices or in the cell centers or the cell edges of a grid. Examples of these grids are shown over here. On the left is the grid for the new NOAA atmospheric model. On the right, from the grid for the European ocean model. And the current generation, and in the current generation of operational forecasting models, the resolution of these grids is about 12 kilometers with about 100 layers in the vertical and then about 30 different physical fields. So if you put the values of the different physical fields at all these grid points into a big factor, it's called the model state, then you end up with a very big factor of the order 10 to the power 12. For data assimilation, there are two popular families. One is the Kalman filter. And the idea behind the Kalman filter is that you reconstruct this conditional probability. So it's the probability that a certain model state X is the true model state given your observations. And it's easier to deal with the condition reverse, and you can do so by applying Bayes' theorem. In this case, this conditional probability, so the probability that you get a certain set of observations given a certain true model state is just your observational error. And we usually assume those observational errors are Gaussian. So Y is the observed value and H is the sample of observation operator that maps your model state to a set of predictions for the observations, with the difference between the two being the observational error. This probability is your background probability. So it's the probability that a certain ocean state was a true ocean state at the previous time step. And then there is the Markov chain assumption that which gives you the probability that your current model state is the true model state given the previous model state. And I'm going to assume that the model is perfect, which means that if I give you the truth at the previous time step, then by just applying the model, you can get the truth at the current time step. Okay, if you put these if you put these Gaussians into this expression, you find that the probability on the left is a Gaussian as well. And by completing the squares, you can find out under the assumption that your model is linear and that your observation operator is linear, you can find out what the mean and the covariance are of your new post-DA probability distribution. The important take-home messages from the slide is that this is the expression for the Kalman filter, which features the among others, the observational error covariance, as well as this B term. And this B term is the covariance of at your previous time step propagated forward in time. And this X4 term is your previous average of the distribution propagated forward in time to your current time. So in a figure, it looks as follows. You start off with your probability distribution at the previous time, which has a certain covariance. Then due to the presence of unstable modes in your model, the spread of your Gaussian increases over time until you get to the time where you got observations and where data assimilation is going to take place. And then in that case, it looks like this. So we've got the previous estimate with a widespread, and then you assimilate your observation that has a certain spread, and you end up with a new shifted probability distribution with a shifted mean and a smaller uncertainty. And then you apply your model again, and then the spread starts growing again. And once new observations come in, you apply data assimilation, etc., etc. There are, however, some problems you have to face if you try to implement the Kalman filter in these high-dimensional operational systems with big model states. First of all, for the Kalman filter, it was assumed that the model is linear. Geophysical models in general aren't. Furthermore, to calculate data assimilation correction, you have to propagate this the B matrix. That's computational intensive, and what's more, because the model state is so high dimensional, it's impossible to actually store this matrix in memory. Lastly, for the calculation of Kalman gain, you have to solve a system of linear equations, and that can also be computational expensive. To address some of these problems are addressed by the Ensemble Kalman filter. And the idea behind the Ensemble Kalman filter is that you take the integrals that define your the mean of your Gaussian distribution and the covariance of your Gaussian distribution, which are shown over here, and then approximate those integrals using a Monte Carlo approximation. And you do so by drawing samples from your previous probability distribution, and then apply the model to those samples, and then take the sample average, or the sum divided by the number of samples, to get your forecast mean and forecast covariance. So express as a figure, you draw the different samples, you run the samples forward in time, and you can do that in parallel. Then from those samples, you estimate your mean and your covariance at the assimilation time. You carry out the data assimilation, and then you continue running your corrected samples forward in time again. Now, the advantages of the ensemble Kalman filter are that it's no longer necessary to assume that your model is linear. You can run all these samples in parallel. Instead of having to store your full covariance matrix, you only have to store your samples, and you can get you estimate your covariance matrix from those. And you don't have to propagate the full covariance matrix, only those samples. However, if you look at the equation that describes the data assimilation update, you will see that the update, which is this, lies in the image of the matrix B. And we use the samples to approximate this matrix. And since we're using only a very limited amount of samples, usually it's between 10 and 100 samples, this matrix is of low rank, which means there are not enough degrees of freedom to correct all errors in your model. So somehow it's necessary to increase the rank of the B matrix. And one algorithm that does that is the local ensemble transform Kalman filter. And the idea is behind the LETKF is that you take a grid point, then you select the observations in the vicinity of your grid point, and then you carry out your Kalman update for that grid point using only the observations in the vicinity. And then you repeat this for each other grid point. Now, the additional benefit of doing that, apart from increasing the rank of the matrix, is that this matrix, the matrix you have to invert, becomes a lot smaller because you're only working with a limited amount of observations, which means that it's easier and faster to invert the matrix or equivalently solve this linear system. Of course, you have to now carry out multiple, calculate multiple DA corrections, but we can do that in parallel. So this is a good way to speed up the process. The only thing you have to watch out for is that because you use different observations to calculate the correction at each grid point, you might end up with a discontinuity in your correction. And to prevent that from happening, you should weigh your observations. The figure over here shows what the weighting function would look like. So X is the grid point for which you want to calculate the Kalman filter correction, and the colors indicate the weighting for any observation as function of space. And in practice, the way this weighting is applied is by increasing the observational error variance in the matrix R. Okay, then the other family of data assimilation methods that is becoming actually, it's the current state of the art, is variational data assimilation. And variational data assimilation is is popular if you use a smoother. So it filters like the Kalman filter I just showed. The data assimilation correction is applied at the same time as the time for which you got the observations. In a smoother, the correction is applied at the end of your forecast, and a set of preceding times. I call this the analysis window. And the advantage of a smoother is that you can, well, one of the advantages of a smoother is that you can assimilate observations at different times, thus use more observations and theoretically generate a more accurate correction. In variational data assimilation, the data assimilation correction to your forecast is found by minimizing some cost function, with delta x being the data assimilation correction and x4 being the forecast. If you're doing 3D VAR, this data assimilation correction doesn't depend on time, so it's constant over the analysis window. If you're doing 4D VAR, it does depend on time within the analysis window. Okay, so to find the 3D VAR cost function, we basically follow an approach that's very similar to the one we used, that was used to derive the Kalman filter. So we're looking for the data assimilation correction, delta x, that maximizes this probability. So that's the probability that the correction is optimal, and by optimal I mean that applying the correction to your forecast would give you return you the true state. So the probability that your correction is optimal given the observations during the analysis window. And once again, we apply the Bayes theorem to swap the order and the conditional. Once again, we assume that the observational errors over here are Gaussian, and that our background probability, this one, is Gaussian as well, with a covariance B. And then maximizing this probability is equal to minimizing minus its logarithm, which turns out to be this function. This function contains two kinds of terms. So there's a penalty term that penalizes any a correction to the forecast, and then there are penalty terms that penalize differences between the observed values and the predicted values for those observations based on your corrected model state. A similar approach will give you the cost function for 4D VAR. However, there are two differences. One, as I mentioned before, the the DA correction in 4D VAR is a function of time. Two, we end up with these new model error penalty terms. So the model error is the difference between your model correction at time t+1 minus what you expect the model correction to be based on the model correction at the previous time propagated forward in time by your model. And Q over here is once again a covariance function, in this case, the model error covariance. The way these, so maximizing this cost function is equivalent to finding the solution for which its derivative is 0, because all these terms were quadratic functions. And well, if you carry that out, then you find that the solution looks like this. So in this case, the factor z consists of your model error, of your model correction at the beginning of the analysis window, plus all the model errors at the different times within your analysis window, with the matrix B consisting of the model, the covariance at the beginning. So there's the covariance for this probability, so the covariance and the probability for the data assimilation correction at the beginning of your analysis window, plus all the model error covariances at later times. And M is basically, the matrix M is the matrix that maps your initial data assimilation correction and all the errors to the full data assimilation correction. So it propagates your solution forward in time. Now, apart from this propagation matrix M, you will find that the 45 solution actually looks a lot like the Kalman gain I showed earlier. But now with factors consisting not just of a single time step, but containing the fields at each time step within your analysis window. In practice, so as you can see, this solution contains once again an inversion, or in other words, a linear system of equations has to be solved. And the way that's usually done is using Krylov methods, especially the conjugate gradient method is popular. And the way it works is that you assume that your initial correction, your initial guess for the correction is going to be 0. In that case, your initial residual is equal to the whatever vector is on the right-hand side of your linear system of equations. In this case, it's called the innovation factor, and it's the difference between your observations and forecast predictions for those observations. Now you normalize that residual, though you don't use your Eulerian norm to carry out the normalization. Instead, you use this inner product that's based on some matrix C1. What the matrix C1 is depends on the Krylov methods you're using and what kind of preconditioning you're using. But for unpreconditioned gain, you get gradient. C1 would be equal to the matrix A that appears in your system of linear equations. After normalizing it, you project the true solution of the system onto onto the basis vector you just created. The issue, of course, here is that you don't know what the true solution of the system is. However, you can, well, by switching to another inner product, you can pull out your matrix A into the inner product, and then A applied to the true solution gives you the right-hand side of the system. So basically you're projecting the right-hand side of the system onto your Krylov basis factor, and that will give you an estimate for the solution to the system. And then once you've got an estimate, you recalculate the residual, orthogonalize your residual with respect to the Krylov basis, and then normalize whatever is left of your residual after orthogonalization to create a new Krylov basis factor, and then using your new Krylov basis of reproject again onto your new Krylov basis, which gives you a new estimate for the solution, etc., etc. So in for the var, the matrix A that generates this system of linear equations is as follows. And this first term is problematic. And it's problematic. What's particularly problematic is the appearance of the matrix M in the term, which because this matrix is computationally very intensive to apply to a vector. And one of the reasons for that is its structure. So you can see that as you go down along the matrix, the number of zero elements decreases. So you have to carry out row, column, inner products with fewer and fewer zeros in them. One way to speed this up is to realize that basically this block of rows is equal to applying one time step to the output of the previous block of rows plus adding your latest model error to it. And that, if you do that, then application of this matrix to a vector will look as follows. You start off with introducing a new kind of field. It's called the adjoint. You start running your joint backward in time. That's this transpose of the matrix M. During that run, you add impulses coming from the vector to which you apply your matrix as forcing into your joint. Then once you get to the beginning of your analysis window, you apply your B matrix to the joint, and now you start off with a forward run. That's this matrix M. And during that run, you add your adjoint as first forcing term to the model. Simultaneously, you take at the appropriate times, you sample the output to generate, using the sample operator to generate the output of applying the matrix to the vector. The problem with this algorithm is that these arrows indicate a sequential process. So it's hard to parallelize. And that's why people have started implementing a saddle point algorithm. And the idea behind the saddle point algorithm is that you split your analysis window, in this case, into two sub-windows. And then you add the adjoint, the value of the adjoint at the beginning of the right-hand side of your first sub-window, and the value of your correction at the left side of your second sub-window to your factor of unknowns. And now you apply this sweep algorithm, but you apply it in parallel to each of the subwindows. So the in subwindow 1, your adjoint run will start off from your unknown adjoint, and in subwindow 2, your forward run will start off from the unknown data assimilation correction at the edge between the two subwindows. Now, so since you can, since the subwindows are only half, cover only half the time of the full analysis window, the time to run each window is reduced compared to the full run, and you can run these windows in parallel. But say, as you have introduced new unknowns, you have to add equations for these unknowns as well. And if you use the sweep algorithm as preconditional, as I just did, it turns out that the additional equations are nothing more than the demand that your adjoint and your data assimilation correction are continuous at the interface between the subwindows. So the adjoint you get from propagating this initial condition in subwindow 2 towards the beginning of the subwindow must be equal to the adjoint which you use to start subwindow 1, and simultaneously the data assimilation you end up with at the end of subwindow 1 must be equal to the data assimilation correction you use as initial condition for the forward run in subwindow 2. Another issue with 4D-var that's currently very, an active area of research is the use is the shape of your covariance matrix B. In the past, it was customary to assume that this covariance matrix B that appears in the 4D-var cost function is static in time and homogeneous in space. And that's probably a bad assumption, as is shown over here. So what we're looking at here is the covariance in the sea surface temperature at this point and the sea surface temperature field. That's shown as a color, as well as the covariance between the temperature and the surface velocity field. Those are the arrows. And this is one of those static covariances, and it works good for the open ocean. But if we now look at this covariance, which is estimated from an ensemble, and it's at the edge of an ocean front, so where the temperature, where the salinity changes rapidly, then we see that the covariance looks quite different. So what we would like is to run an ensemble of 4D-vars and then use that ensemble to estimate the covariance B, just like is being done in the ensemble covariance, in the ensemble Kalman filter. Now this requires that you apply 4D-var to each ensemble member. And just as a reminder, so you apply 4D-var to each ensemble member, which means you have to solve a linear system for each ensemble member. And just as a reminder, you do so by projecting your right-hand side of the system onto a Krylov space. And of course, the bigger the Krylov space, the more accurate your solution for the linear system is going to be. So you want to increase the size of the Krylov space. Now, if you run an ensemble 4D-vars, the trivial, straightforward approach to do is to just apply 4D-var separately to each ensemble member. And if you do so, and you look at the Krylov space of each ensemble member, then after your first Krylov iteration, each ensemble member has a Krylov space of dimension 1, which was obtained by normalizing the residual. After 2 iterations, it has a Krylov space of dimension 2, and yeah, well, etc., etc. Now you can run the 45 for each ensemble in parallel, no problem, but it will take just as much time as running a single 45. It's just that you need a lot more computational resources because you have to do it from the whole ensemble. It would be beneficial if you could exploit the fact that you're running a whole lot of 45s to reduce the number of iterations, because in that case, you would also reduce the time you need to create the 45 correction. And that is where the EVAL, the Ensemble Variational Integrated Localized 45 comes in. The idea behind EVAL is that just like in the previously outlined method, you start off for each ensemble member with a residual. You normalize that residual. That involves application of a matrix to the residual, but that can be done in parallel. And then you end up with a whole set of Krylov basis functions, basis factors, and the idea is that before you start to project your residual on this Krylov basis, you throw all the Krylov basis factors you get from the different ensemble members to create together to form one big Krylov space, and then you project the residual of each ensemble member onto that big Krylov space. And because, and in this case, the Krylov space you're using to solve your system after the first iteration is of the same dimension as your number of ensemble members. After the second iteration, it's twice as big, etc., etc. So it's larger than in the previous approach, which means that in all likelihood, you're going to get convergence and fewer iterations, which means that you're speeding up your 45. Which brings me to the summary. So data assimilation in operational forecasting models is difficult because the model state in these operational models is so large that you can't store any matrices of that work on the model state explicitly into memory, and the calculation of matrix, the application of matrices to vectors of that size is computationally and time intensive. To overcome that, parallelization schemes have been implemented in the different data assimilation methods. So in the ensemble filter, the background covariance B is approximated using from a limited set of samples, and each of those samples can be propagated forward in time in parallel. In the LETKF, the DA correction is calculated separately for each model grid point, and that calculation can be carried out in parallel for each grid point. In saddle point algorithms, the analysis window has been divided into separate sub-windows, and the application of your matrix for each sub-window can be carried out in parallel. And in EVAL, the the different Krylov space basis vectors can be generated in parallel, thus allowing for the use of larger Krylov spaces. Now, if you're still interested in data assimilation, just not that much in the equations, the department over here has just released a free online DA course, which can be found on this web address. I want to thank Schmidt Futures for funding my position over here. And then I think I'll take questions, but not in parallel, please.
All right. Thank you, Ivo. So let's thank Ivo for this wonderful talk. Thank you so much, Ivo. So at this time, I'll open the floor for any questions. Does anyone have any questions for Ivo? Okay, I'll start with the first question. So for any of those DA schemes, what models are they best used for? I mean, do you have any examples from the top of your head that you have used those DA schemes for?
So so in general, the opinion is that, I would say the opinion is that variational 4D data assimilation is superior with respect to producing data assimilation corrections. And that has to do with the fact that it allows for the use of smoothers, and smoothers don't suffer from the effect as much that that you get jumpy corrections, and this is in particular problematic for things like precipitation, because if you make a strong correction at one time, then maybe because you reduce the temperature, your humidity in the atmosphere starts to rain out, and then of course, if you after that increase the temperature again in your Kalman filter, then that humidity doesn't come back because it has rained out, and using something like a smoother prevents these jumpy corrections from happening. So yeah, but a smoother 4D is a lot more computationally a lot more expensive, and that's why Kalman filters see still a lot of use. And in addition to that, the Ensemble Kalman filter is able to. So the Ensemble 4D is something new, and it has this benefit that it includes the errors of the day into the B matrix, and Ensemble Kalman transform has had this for a long time, so that those less computational demanding and the ability to capture errors of the day were the benefits of the Kalman filter, but generally the 4D VAR gives you better results, better corrections.
Okay, so I have a follow-up question. So I mean, so can you think of any examples from the top of your head, like ocean models that you use those for?
So ocean models, I know that the Oregon one uses 4D VAR with a static covariance, and I know the European Center for Medium Range Weather Forecasting uses 4D VAR for its atmospheric model, but I think 3D VAR for the ocean model, and I know that the US Navy uses 4D VAR in its ocean model for mainly research, and 3D VAR, I think, is running operationally.
All right, thank you. Are there any other questions for Ivo?
Let me stop the recording.